Alexander Hamilton. My name is Alexander Hamilton. Hey, what's up, guys? I'm here with day 24. Shout out to those of you guys who got to go to see Hamilton today. Just know that I am really jealous. All right, today we're going to look at more implicit differentiation, but we're going to mix in the chain rule a little bit. So what I want to do is I'm gonna go through three problems. One, just find dy dx. One, find the slope of the tangent line. One, write the equation of the tangent line to the curve. So let's start with the first example. We have this function, or not function, I keep saying function. We have this curve. So take a look at this one. Our goal here is simply to find dy dx. When we take a look at this, a couple of things we see. Again, we see x's and y's. We should be used to that now with implicit differentiation. What's a little bit different here is we do see a function, y cubed, within another function, sine of x. So we're going to have to use the chain rule to do this derivative. We also have to pay attention to the fact that we will be doing a derivative of y in there. Also, we see another product rule there with that minus xy. The only thing that's nice about this is that we have 4, a constant, on the right side of the equation. So why don't you take a pause in this video and try and solve this one on your own. See what you can do. Give it a whirl. Take your best shot at it, and then come back and see how we do it. Okay, we're back. So I see a function y cubed within another function sine. So I need to execute the chain rule. So I'm going to do the derivative of the outside, which would be cosine, but with respect to the inside, y cubed. So I start off like that, derivative of the outside with respect to the inside, but now I need to multiply by the derivative of the inside. And that derivative is going to be a derivative of y. So I'm going to end up with times 3y squared dy dx. So there we have the first one. We'll clean that up and make it look a lot nicer, but that's what we get going through the process. Now I have to do the product rule here. Notice my two functions. I always like you to underline them just to make sure we remember that we're doing product rule here. I want you to think of the first function as negative x, the second function as y. So I'm going to do the derivative of the first, which is negative 1. I'm not going to write the 1. So it's going to be negative 1 times the second, which is negative y. Again, product rule is plus, but I'm going to add the first, which is negative x. Instead of writing plus negative x, I'm just going to anticipate that and write minus x. So that's the first, and I need to multiply by the derivative of the second. So I did the whole product rule. I did the derivative of the first, negative 1 times the second y, plus the first, negative x, times the derivative of the second, dy dx. And that's going to simply equal 0. Derivative of 4 is 0. I want to take 1 second to clean this thing up a little bit before I start solving. I'm going to go ahead and put my 3y squared in front of my cosine of y cubed, dy dx, minus y minus x dy dx equals 0. Okay, so now I went through and did the derivative of everything. I got everything looking nice. Now I just want to get dy dx by itself. Well, that'll be easiest by just adding y to the other side. Now I want to go ahead and factor out my dy dx. So I factor out my dy dx and then divide over my 3y squared cosine y cubed minus x. Right. And there we have it. That is dy dx. I wanted to take a look at what this curve actually looks like. So I went to Desmos before I made this. And I'm just going to look at the graph of sine y cubed of minus xy equals 4. So let's go back and see what that looks like. And there you have it. That is kind of a funky looking graph there. All right. Kind of trippy. Anyways, just thought it's kind of cool to look at what it looks like. Okay, next, let's try another problem. My function now is cosine of xy plus 3y equals 10. And what I want to do is I want slope of tan line at the point 0, 3. So I want to look at the slope of the tangent line to this graph at 0, 3. Okay, so slope of the tangent line, again, I need to find dy dx, then I just have to plug in the point 0, 3. So let's go ahead and do this, think about this derivative. Once again, I see a function, xy, within another function, cosine. However, what's trapped in there, that xy, is going to require a product rule to do the derivative of it. So this is a product rule within a chain rule. But we're just going to have to fight through it and figure out the answer. Here's what we get. We need to do the derivative of the outside with respect to the inside. Notice I did not do the derivative of the inside, because that's not what we do in the chain rule. Now I need to multiply by the derivative of the inside. Well, the derivative of the inside is going to require the product rule. So I'm going to do the derivative of the first. Right here are my two functions, x and y. The derivative of the first is 1. I'm not going to write 1 because we're in AP Calculus, times the second, y, plus the first, x, times the derivative of the second. And now I've successfully completed the derivative of cosine of xy. I'm still not done with this problem, but I got a good start on it. Now I just have to go and do the derivative of 3y. Well, that's going to be 3 dy dx. And that whole thing is obviously going to equal 0 because the derivative of 10 is 0. Okay. Now we have to figure out how we're going to get dy dx by itself. And one way that we can address this problem is we can distribute that negative sine of xy in there. It's not the only way to solve this problem, but it was my first instinct in solving it. Now when I distribute this, I want to write polynomial stuff first, or coefficients first, polynomial stuff second, trig stuff third, dy dx stuff last. So here's what I end up with. So right there I see negative y sine of xy minus x sine of xy dy dx plus 3 dy dx equals 0. You got to be really careful here. It's really easy to make a mistake in this particular unit. But if we're careful and we just are really conscientious while we're doing this, we can make sure we get it right. Okay, now I've got dy dx's in the second and third terms there. So I want to take that first term and add it to the other side. Those of you who are kind of reckless with your negative signs, this could be a challenge for you. So let's help ourselves get better at this. Right? When we move that negative y sine y xy, when we move it over, it becomes positive y sine of xy. All right, now let's factor out our dy dx and divide. I'm going to do that in one step here. And I want you guys to start doing this move in one step as well, if you're comfortable. And we see that move right there. So we got dy dx equals, and again, if you don't see where I got that from, just factor out dy dx like you're used to, and you'll get dy dx parenthesis negative x sine of xy plus 3. You divide that over. All right, we'll just save a little bit of time. Now, that's our derivative, but we're not done with the problem. The problem says we want to find the slope of the tangent line at the point 0, 3. Right, so we're working with the point 0, 3. You guys did a great job. We didn't look at this in the last video, but a lot of you guys figured out how to do it just intuitively, which is awesome. What I want to do now is replace all of my x's with zeros and all of my y's with 3's. So I'm going to get 3 sine of 0 times 3, which I'm just going to put in as 0, over negative 0 times sine of 0 times 3, which is 0, plus 3. So what do we get out of this? Well, we know that sine of 0 is 0. We better know that. 0 times 3 is 3, so we get a 0 on top. This whole term right here, since sine of 0 is 0, becomes 0. 0 plus 3 is 3. 0 over 3. Don't freak out because you see the 0. 0 is fine on top. We get a problem when it's on the bottom. Right? Then we'd have a vertical tangent line. So we get a derivative answer of 0. So that means the slope of our tangent line at that point should be 0. Let's take a look at the graph here and see if that actually kind of matches up. So here's our graph of cosine of xy plus 3y equals 10. Here's the point 0, 3 right here. Does that look like a horizontal tangent line? A slope of 0 with the tangent line? Well, it sure does to me. Right? So the picture here kind of matches up with it. Once again, we see kind of a cool looking function. Again, not function, a cool looking curve here. It's not a function. It fails a vertical line test in a lot of different places. Over here especially. Okay, let's look at the last one for today. Here's what we have. For this one, I want the equation of a tangent line at x, or at the point 2, a fourth. So whenever we're asked to find the equation of a tangent line, we need point and slope. The nice thing is, our point we already have. We know the point is 2, 1/4. All we need to find is the slope and then write the equation. So let's go ahead and do this derivative. Once again, I'm going to see a chain rule because I have x squared y within the function ln, natural log, but I'm also going to have another product rule on the inside there. So when we do this, I'm going to get, for my derivative, 1 over x squared y, that's the derivative of the outside with respect to the inside, times now the derivative of the inside. Well, this is going to be a product rule, x squared and y. So the derivative of the first is 2x, times the second is y, plus the first, x squared, times the derivative of the second, which is simply dy dx. And I'm done with the chain rule and product rule there. Plus 4 equals 0 would finish that off. The last two were pretty easy. Okay, I'm going to clean this thing up a little bit before I try and get dy dx on its own. I'm just going to put all of this on top of the fraction. So I got 2xy plus x squared dy dx over x squared y plus 4 equals 0. So I got to get dy dx by itself. A couple of things here. I'm just going to move that 4 over right away. And I'll have 2xy plus x squared dy dx over x squared y equals -4. And I'm going to multiply over my x squared y, and I'll get 2xy plus x squared dy dx equals -4x squared y. I'm going to subtract away my 2xy. And then I'm going to divide by my x squared. So we see -4x squared y minus 2xy over x squared. Any simplification I can do here? Again, if you don't see the simplification, that's okay. We're going to be plugging in here, and it's going to work out just fine anyways. But we can save ourselves, we can make the plugging in a little bit easier if we do our cancellation here. Potentially. So what I notice here is the coefficients can't cancel. However, I could take out an x from every term. So I can do that move right there and get -4xy minus 2y over x. Now I just need to plug in my numbers. And again, we're evaluating at the point 2, 1/4. When I do that, I get -4 times 2 times 1/4 minus 2 times 1/4 over 2. I want to get this thing down to what it should be. I'm going to go ahead and take those out right there. 4 times a fourth is 1. So this is going to equal -2 minus half over 2. I want to get rid of that fraction within a fraction. So I'm going to multiply the top and bottom by that denominator of 2. And we're going to get -4 minus 1 over 4, which is -5 over 4. So our slope should be -5/4. So that makes my equation y minus a fourth equals negative 5/4 x minus 2. So let's take a look at that one on the graph too. So here is my graph. The natural log, right in a really weird curve here. Got the natural log of x squared y plus 4x equals 8. Now let's graph my tangent line and see if it actually is a tangent line. Notice the tangent line should be, the point here is 2 comma a fourth. So that looks like that's going to be right. Let's go ahead and graph it. Y minus 1/4 equals negative 5/4 parentheses x minus 2. And right there we see a really nice illustration of what a tangent line looks like, coming in and nailing that point right at 2 comma 1/4. That's it for today. Can't forget my outro. 2 chains. See you guys. Have a great weekend.